Lorenzo is an assistant professor at the University of Messina. We have, as I mentioned at the start of this event, he is a frequent contributor to Flower, so I'm delighted to have him back here. And I've always thought that there was a huge potential for federated learning and robotics to work together more closely. So I was delighted to see the work he's been working on. I think he told me about this work all the way back in March. And so I'm really interested to see how far it's gone. I haven't seen much work of this kind yet, so he's really blazing a trail in this direction that I hope others will follow. So Lorenzo, thanks for joining us, and we're very excited to see what you have for us today.
Thank you, Nick, and all the community. Let me share the screen. I share just the window. Let's see. How can I do it? Window. Okay, let's share the entire screen. Maybe it's better. Can you see something? I think not, right?
Not yet.
It's not stuck the button. The share button is stuck. You cannot do nothing.
Do you think it's your end, or do you? I'm just looking at the settings. I think we're fine.
On my site, I can try to leave and enter again.
Yeah, maybe do you want to do that? I'll we can
I'm sorry.
Sure.
And so in the meanwhile, hi, can you hear me?
Yes, I can hear you fine. So we're good. Do you
Yeah.
do you want to try sharing just to see if that's working
sure,
fine?
because there are lots of like so entire screen and preventing access. Your browser is preventing access to your screen. Oh, I think we had
So you might yes, I think there's a setting involved there, but at least we've made progress. You can share your screen now. You can share your video. We can hear you. You can hear us. That's great.
But I think this is a problem. I can't install this client side Zoom. I still work using this browser. I don't know. I had some problem with permission because the laptop that I'm using from the Institute. So I think it's still.
I think under settings, there's an option to enable the browser to share.
In the settings of here, or in the settings of Zoom, or
within the settings of the operating system.
Okay. I usually use these Teams for the.
How about you stop sharing, and we'll hear from Lorenzo. And in the meantime, I think if you explore your settings, you should be fine.
Okay.
Can you see my screen?
Yes, I can see your screen.
Okay.
Yeah, everything looks fine.
Sorry for the interruption, but I tried technically.
No problem. So over to Lorenzo.
Okay. So thank you so much again, Nick, and the whole Flower community for this opportunity. So I'm gonna talk about our interaction between federated learning and robotics, and specifically the ROS framework. Let me say just something about me really quick and the research group. So I'm currently an assistant professor in the University of Messina. I work at the cross of distributed systems and artificial intelligence, and my research has really application in many fields like smart city, healthcare, natural disasters, and so on. So Messina is really in the heart of the Mediterranean. So we have it's the piece of the land on the left, and we have also the opportunity there to have different applications for our use cases. And this is part of the group in a funny moment, and we are a lot also because we have the opportunity to have different projects going on. This is just a selection of the most important projects we have right now, a research project like the European one. And let me just focus on the TEMA one, because the presentation that I'm doing comes out from some idea that is from this project. TEMA is about natural disaster management. Specifically, the University of Messina is working on providing distributed artificial intelligence for running artificial intelligence applications, but also for improving the orchestration and offloading. So federated learning is there inside for these two reasons, let's say. Then, I mean, the reason that I'm discussing today is mostly an application reason for robotics. This is the normal contents that we typically have. The introduction is about federated learning. I will not discuss it. I think we are on the same page. But what is really important now, and I will focus from my own, is to discuss about federated learning in robotics and what is the research trend. If we look on Scopus, is one of the most important database for paper. We can see that the first paper is of 2018, and there are not so many papers, 123, but the trend is growing a lot. So in the 2023, there were really so many papers, so it's exponential, the behavior right now. We read some paper about it, and we are, I mean, we know enough about the utilization. Most of robots application today are about drones, mostly for military, but also civil applications. And federated learning is used for the optimization, sometimes for resource allocation, sometimes for communication. There is really some problem with robotics. The first one is that even if there are many frameworks about federated learning, and Flower is one of these, one of the best, still this really doesn't work if we want to maintain real ROS communication. What is ROS? ROS is the software that roboticians typically use. It's the robot operating system. It's not really an operating system like we know, like Ubuntu, Windows, and so on, but it's mostly a middleware to interact between the hardware and the high-level services. ROS2 uses an internal communication system. It's called a data distribution service, and that's why our idea was to somehow starting from scratch a federated learning framework for ROS. We call it FedROS just to give a name to this one. It's anyway a good name in this case, and this enabled the possibility to have the learning jobs on ROS devices, so drones, rovers, humanoid robot, and so on. The other thing, and we will see why, is that we needed a way to create federated learning jobs. And so we thought, and our distributed system background come out in this case, so we created a kind of platform as a service for creating federated learning jobs. So that's the methodology, and this is also something that we in part already shared with the Flower community in the Flower AR Summit this year. The idea is this one, to have different inputs, are the common inputs that we have in AI projects. So of course the data set, the creation of a model, loss function, optimization function, and then all the hyperparameters in a configuration file, battery, input, output sites, epochs, momentum, and all the other hyperparameters that are needed. In the middle, we see the ROS components. ROS is built in using ROS packages. Inside the ROS packages, there are multiple ROS nodes. Each ROS node should be dedicated for a specific application. Typically, one ROS node could be to move to use the motor of a well, or to sample some data. In this case, we created some ROS node for the training on the client, and some ROS node for aggregation in the learning, in the federated learning server. Of course, the client one is not just one block, but is multiple blocks. We have, of course, multiple clients. what you see written there is the normal algorithm of federated learning. In the output, we have the global model weights when we need to make the aggregation, or just the model when we are ready for the prediction. Let's see how we create the job. So what is the process for creating the federated learning job? So first of all, we create a manifest. It's a YAML manifest. So the FedROS user implements the model. We will see some example, the optimizer, the loss function, and so on, by extending abstract classes. On the right, we can see an example of federated learning job recreator manifest. We have the strategy. I don't know if you can see the mouse. We have the strategy here to select the number of clients, other parameters for federated learning, like the number of rounds, then model, optimizer, and so on. Also data, where they are, other parameters about data. Let's get an insight on each of them. So the model needs to be built using a standard class. What does it mean? We need a specific model, a specific name for the class, and a specific name for attributes and methods. Why? Because given that we are injecting from the external world the models and loss function, optimization function, and so on, really the application that will assemble all these components doesn't have idea what is inside the model. But this application knows that there is the model class, there is the forward class, and we will use it. So we are trying to really abstract to the an high level position the entire components. This one will be stored ideally in a task repository. For testing purpose, it's just the file system. Loss function is like this, so maybe it's much more clear what is the logic of the creation of these classes. Loss function is always the name of the class. Then I used the builder pattern here. I prefer it just for to be more clear in the implementation. In the builder pattern, you can see the creation, in this case, of a cross entropy loss, which is called the loss function, and we get this loss function with a get method. Same stories for the optimizer. You can see here more methods because they were important for building the loss function. And then we have here an example of configuration files. So it's a YAML or a JSON file where there are, the hyperparameters needed for the application side, but we have also some information which is important for ROS. This is something that we are going to move in a, let's say, default configuration file, a system configuration file, so the user cannot modify it, they cannot really change the behavior system. What is at the end the goal of having all these different files? It's assembling the client. Why we have to assemble the client? Because we will see ROS needs to be built. This is the most pain point that we have with ROS. Building means that we need to know everything a priori, and we need to build all these classes, in a building phase. We created then two different nodes, in this case, the training node for the client and the interface node. The interface is important because when a ROS node communicates with other ROS nodes, does it using a specific message, and this message is reported inside this interface file. We will see some example. I just give here some introduction. So the point is copying the file in the destination path. So we copy the model inside the training, the loss function inside the training, and all the other components. In this way, we build the ROS package, and we put everything in a Docker container for an easy deployment. This is, some piece of code from a Docker file, dependencies for ROS, and we can see here the building phase. So the Colcon is an application that ROS use, and then we have the running. So at the end of the system, at the end of the building, we can run the application. It seems in some way easy described like this, but we have two main issues. Because the design seems fine, but when we move to the implementation, we have to consider two things. The first one is that, as I said, the ROS needs to be built in runtime. So that means if we want to have something dynamic, parameterized, I mean, something that following all the object-oriented programming needs to be reused in the future, we should need, we should rebuild applications many times, and we should build an application for each kind of neural network we want to implement. So that's why we should know a priori what is the application, but really in our case, we don't know a priori what is inside the manifest. So we need to create some kind of application that is able to abstract this process. The second problem is the communication problem, as Arnold said already. So ROS uses this DDS communication publish subscribe. The interface message should be defined a priori before the building phase. But this is like saying that we know what are the weights matrices, but we don't have any information about the model. So this is something that we cannot do. This is an example just to give you an idea about what is a message in ROS. These are two different messages. The first one is this one where we have to define the type of the variable and the name of the variable. Then there are here other kind of messages. You can see this X is a float 64, while this sequence is a unit 32, stamp is a timestamp, string, and so on. Why this? During the building phase, this file, which is just a text file, is translated in a C++ class, and each of these variables is accessed with the dot notation. So it's really complicated. It was really a mess to try to build this kind of file for all the neural networks that we create. So what is the solution that we imaged? So the first one is to make a composition, the composition of the training and the aggregating. Of course, when we make the composition of the first training for the federated learning client is the same for all the clients except for the dataset, of course, which will be different. When we talk about the aggregating for the server, it's of course just one single instance, and that's fine that we create this. When we talk about the interface, even in this case, we want to create the interface message in runtime. How? Extracting the information about the weights in runtime. So that means we need to load the model. We need to read inside the model all the type, all the layer shape, the number of parameters, and we have to do it before of the building phase. This is an example of interface message if we have a convolutional neural network, just a simple one, and this is programmatically written, okay? This file is not written by a human, but is written by a program. And we can see that we extracted that this is an array in float 64, and this is the name of the layer. And we have, I mean, the information for all the layers. I have really a quick demo that can help to understand what we are doing. I will jump on the important moments. You can see here on the left, I mean, the file system. We have the Federos client and the Federos server. These two packages are not self-sufficient, as I said. We need to inject the model, loss function, configuration file, and so on. So when we run this script, and the manifest was the one that we saw at the beginning, you can see now on the left that everything is copied. We have now the loss function, the models, the optimizer, and we have on the Federos server side the config, and inside the node folder we have the aggregation algorithm. So there is a moment when the Docker containers are created and the application are built. As soon as we don't need anymore the files, we just clean it up. So we don't need to dirty them in the system, but they are already built inside the application, inside the Docker container. The Docker container is now building the ROS nodes, the interface, the training, and also the aggregating. Let me jump now here where the training already started. We have just 5 rounds and 5 epochs. We can see that the system is learning, reducing the loss and increasing the accuracy. I just jump at the end, and we can see that it's working after 5 rounds. This is not just to see how the training is going, but to see that the system is working. Let's see now some result. And I have some result where the testbed was just a MacBook Pro M3, so last generation. And we have results both from the composability, so the assembly of the system, then also from the federated learning point of view. About the assembly performances, we try to focus on the most important and most the part that needs much more effort. This is about the get model architecture. In this moment, we before the building, we access the model, and we try to read from the model programmatically the number of the layers, the name of the layers, number of parameters, and the shape. And this is important to write the interface file. We really tested the system. In robotics, it's a bit complicated to have something like 10,000 of clients. And even if we have 100 clients, if they are drones that are running in the same area, this is really complicated to have 100 drones. But we can see that the system is, for this kind of numbers, really working good. So we were able to have in 1 second 100 clients that were built, and if we just increase, it's still done in 4 seconds or less than 5 seconds, 10,000 of clients. When we come to the creation of the interface, it's just an input-output operation. We have to write this message file. This is done really in a short time. It's 0.005 seconds or more or less, but when we increase the number of clients, it's just 0.01, more or less. And this is about the creation of a deployment manifest that we did just for testing purpose. Of course, when we move in production, let's say, we cannot work, of course, in a single machine, but we have to redistribute to different machines, so different drones, different robots. But in this case, for just creating this file, at the end of the day, the process will be still to create a file, but with the remote connections. We have input-output operation that grows more or less linearly, something exponentially, but it's in the order of 2 seconds for 10,000 of clients. One of the big issues that we have is the size of the container. The ROS container alone, Iron is one of the last versions of ROS, is already 700 megabytes. When we install the dependencies, we just increase not so much, but then when we install also the Python free application dependencies, not only the ROS one, but also the application one like PyTorch, we use PyTorch, and also the application, it grows up to 1.5 gigabytes, more or less. So it's not really an issue to have 1.5 gigabytes in a drone or in a robot. Okay, of course we have space. The issue could be in distributing this kind of application, because we need a time to download the whole application, so to pull the container, and the provisioning, the deployment could be something that we need to take care about. Then we have some tests on the federated learning side. So we run one model, a convolutional neural network with the layers you can see on the left. And we use the standard MNIST. In this case is IED sample dataset. We have for the federated learning the training set with 2,000 of images and the test set with 333 images. With the benchmark, we just summed all of them because we have 3 different clients. We have 6,000 and 1,000 of images for the test. What is the goal for this kind of test? The goal is understanding if the federated learning approach for robotics is working. So we want to equalize the accuracy of the proposed approach, the FEDROS, with a traditional approach. So we want to overlap the curves of loss and accuracy. But at the same time, we want to see an improvement in the computation time, because we are parallelizing the computation. It's not done in one device anymore, but it's done in multiple devices at the same time. So we want to see some better result in this case. So we used 3 different Raspberry Pi clients, so microprocessors. We really underestimated the system because typically a robot can have also some device which is a bit better. For instance, some NVIDIA Xavier or NVIDIA Orin, so with some mini GPU inside. We can see for the training dataset that the loss in the accuracy for the federated approach and the traditional approach is overlapped, so we have a good behavior of the system. The same we can say for the test. Of course, we have a bit more fluctuation, but the system is working quite good. And we can say also that we have an improvement in terms of computation time. So if we run the traditional approach on a Raspberry, we get more than 1 hour. If we run on 3 different Raspberry using the federated average algorithm, we really decrease of more or less 50 minutes. Okay, so we have the application in 23 minutes using a Raspberry, and we can really also reduce the number of epochs because the 95% of the accuracy was reached in 50 epochs. So that means we can have also a time which is minor. Let me go to the conclusion, just to say that we try to fill a gap that we encountered right now in the literature, in the state of the art. So a way to have a federated learning in robotics using robotics software systems. Okay, it facilitates the submission in this case of federated learning jobs. We have still a lot of work to do in this case, but the first demo, the minimum viable product, let me say, is quite usable. In the near future, we want to do these kind of things. First of all, testing with different networks. Okay, one of the issue we have right now, I mean, it's not really an issue, but we just tested with all this convolutional neural network. We want to test with different kind of models and different kind of data sets, both ID and non-ID, to see what happens. ROS has also a different paradigm other than the publish-subscribe. There is the client-service communication. It's more an asynchronous approach, which is much faster, so we can maybe get some an advantage. And the other thing is simulating on a real distributed environment, so could be a swarm of drones. The other point is trying to understand if we can really use a framework that has a good community on the back, like Flower. I mean, we don't want really to reinvent the well. I mean, we had the need to program from scratch because there was nothing that used the ROS publish subscribe communication system, but could be really important to be, I mean, in the game of the federated learning that today everybody's playing, and then using some framework that already exist. Because the possibility was with Flower at the beginning, and I mean, we can maybe open a discussion, Nick, I mean, the other guys, that we can discuss now or offline, that we can use ROS also with normal HTTP communication. If I remember well, Flower used gRPC or something like this. But we are not using really the ROS communication. So we should understand what is really important also for roboticians and what could be better for robotics in general in this case. So this could be something in the future. Why I'm talking often about drones? Because on the European project, we have the possibility to talk with end users, so to make some experiment. In natural disaster, drones are often used to look into the disaster, typically later the disaster, after the disaster, looking for objects, looking for humans, looking for cars, buildings, other kind of stuff with pictures and drones. Federated learning and drones is an interesting match. We thought at the beginning that we could try to have any kind of algorithm inside, but maybe supervised learning is a bit complex because that means that while the drone is flying, we should also label the new samples. And this is something that technically is doable, but seems unrealistic. So we are exploring also some unsupervised approach in this case. So this is all. Thank you for to the audience for being here. This is a bit of bibliography about the presentation, and now I'm open to any question.
Thank you so much. Very interesting work. Let's see if there's any questions either on Slack or for people who are here locally. Yeah, if there's any questions, we can take them. Let me take a look in Slack in particular. Yeah, I guess one question, I think you were answering this, although I also didn't seem to hear a sort of a clear answer on it, which was when do you think we could actually use this on a piece of on a drone, for example, on a robot? The question was saying when do we anticipate seeing this deployed onto a robot of some kind?
Yeah, there are different, I mean, let me say it's not really easy. We are discussing also with the robotics community for this reason. Robotics community sometimes has also some issue in terms of distributed systems, but is really good in AI. So we are trying to make a match in this case. One point is, and it's something that we have to really validate. So the drone, of course, when is there for the natural disaster, needs to be up and running. So the model needs to be there immediately. We cannot wait that the federated learning start from scratch a training and a model. So that means there is already a pre-trained model that is doing its job, which is recognizing people, humans, objects, and so on. But at the same time, we can fine-tune this model with the geography of the land, new pictures, the specific disaster, and so on. So this is something that we can do at the same time. So there is a thread that is doing the prediction, a thread that is doing the sample, and at the same time, this sample is trained in a federated learning approach. So this is something that we want to try. It's really challenging, because the drone is probably the most complicated element in this case for robotics and federated learning, because the drone is battery powered, and the drone in average flies for 20 minutes. So we don't have really so much time. So we are trying to understand if we can do everything in less than 20 minutes. Then the drone needs to be back to the base station and to recharge. The base station is, in our case, also the aggregator. So if you fly like free drones, there is a base station, which is a laptop, a computer on the field that collects your data and is used to control it. And also from the regulation point of view, because from the regulation point of view, during a disaster, a drone cannot fly, at least in Italy where I live, but in Europe, more or less, is like this. That means it shouldn't, and also cannot be autonomous. It's really dangerous right now. So we are really looking ahead in this case. It's really a research approach. So we are looking what we can do, understanding if using this kind of device could be safe for humans and for first responders, so civil protection, firefighters that are there to help. They don't need to be distracted by this kind of stuff. Today, having, of course, one person per drone is not scalable, because currently, if you have 100 drones, we need 100 people. I mean, it's not doable, that's clear. So this is one of the cases that we are investigating, because we have, a project here. But I see also good application in social robotics, industrial robotics, where, the situation, let's say, it's a bit more easy. We are not in a disaster. We don't need to have sometimes, mostly in social robotics, a real-time decision. We can do it with a bit most of relax, let's say. So there are cases where this application is less constrained. And this approach is good for any kind of device that can install ROS. Okay, so drone is one example, but there are many of these.
I see. Yeah, we actually there's a few more questions there, but we've ran a little bit over time. So yeah, thank you for the talk. It's really interesting, and I really look forward to tracking how this goes and where it sort of heads to next. I think there's also a lot of interest in the community for this. You mentioned a lot of people using ROS for a variety of reasons, I think on some certain embedded systems and so forth. So this capability, I think, will be warmly received. Yeah, so thank you again. Thanks so much.
Yeah, thank you so much.